Okay. Howdy. Um, Unfortunately, we cannot meet in classroom anymore. But the semester is not over, so we have to go over like all these materials. So like from this week, and I will provide like the lecture video, like the lecture videos for each topics. Okay, so it's not weekly schedule, but like we're gonna try to cover all the material that we have to study. Okay, so well, please watch the video first and try to catch up like the material first. Then you have to bring your questions, or like we can discuss couple more extra problems during the class time. Okay, as I sent you, like you have to use the Zoom link like to attend the classes. Okay. So, okay, let's start. First of all, we talked about one important application problem, okay, which is vibration motion. Where basically the reason why we talked about this one is like this model is homogeneous or non-homogeneous second order linear differential equation with constant coefficient, okay? That's exactly what it learned before. And to solve those problems, we have to use the characteristic equation, right? That's what I learned. And we're going to talk about like, how we can apply the technique for this problem, okay? And during the very last class, we talked about how we can derive the uh, differential equation for vibration motion, right? So maybe we can start from here, okay? As you talked about it, there's like four different force. The first is weight. The second one is spring force, and third one is the damping force, and the very last one is external force. Okay, when you combine everything, then you will have this equation. Okay, so like this is second order linear differential equation. Okay, or m gamma k's are like positive constant. Okay, that's really important part. Okay, that's why we can use characteristic equation to solve this problem. Okay, so that's why we talked about it. And today, even we covered everything, all this material, but already. But I would like talk about undamped free vibration motion again. Okay, undamped means there's no damping term, which means the gamma is equal to 0. Is okay? And also, like we assume like there's no external force as well. Okay, then we will have like this form. Okay, like mu double prime plus ku equal to 0, and that's exactly a homogeneous second order linear differential equation with constant coefficient, because m and k's are all positive constant. Okay, so we'll start from here. Okay, but like just think about the motion. Okay, it is vibration uh, differential equation for vibration. So basically, like you have spring is hanged on the ceiling, and then there is like something hanging on the spring, and you just like stretch a little bit and let it go. Then what happened is up down up down up down, which is oscillation motion. Okay, but if there is damping force, then definitely that motion will be like getting slower, and finally it will be stopped, which is equilibrium position, right? But if we assume there's no external force and there's no damping force, then like that motion would be continue forever. Does it make sense? So like from this one, in mathematically, we can assume like this way. Basically, it's oscillation motion, right? And one of the like mathematical function is concerned with oscillation motion, which is the trigger function, which is sine or cosine. Okay. So we assume like your answer would be sine and cosine form. Okay. That's what we're gonna do for this class. Okay. So okay, here we go. Since it's second order linear differential equation with constant coefficient, and we can solve this problem by using the characteristic equation. Okay. Here we go. Let's start from here. Which is mr squared plus k is equal to 0. And let me subtract k on both sides. M r squared is equal to minus k. Let me divide by m on both sides. Then r squared is equal to minus k over m. Okay, but keep that in mind, as I told you, m, which is mass, and k, which is spin coefficient, those are all positive number. So your right hand side is negative now. And we're going to take the square root on both sides. And what will happen is you're going to have like negative number under the square root, okay? Then I can say your r is plus and minus square root of k over m I. I is equal to square root of negative 1, right? Then if I define new variable omega with square root of k over m, then my r can be written by plus and minus omega I. Okay, this is much simpler and easier notation. That's why we're going to use this notation. Okay, so like since we find r, then now we can find the general solution for this differential equation, right? Do you remember, like whenever you have like imaginary number, they must be cosine and sine combination form. Okay, here we go. So finally, the general solution is let's say ut is equal to constant a cosine omega t plus constant b sine and omega t. Okay, so a and b's are arbitrary constant. Okay, so look at that. As we expected, as we expected before, since it would be the oscillation motion with a, like something period and like uh, frequency as well. Like that's why like it must be the form of the like cosine and sine function. But if we have like this form and it's not easy to figure out the frequency and period or amplitude or something like that. Okay, so that's why we have to try to make it as one single trigger function. It's like cosine. So that's what we're gonna do. Okay, so what we're gonna do is we will define new variable r and delta, which is defined like this way. Okay, let me say for some arbitrary or like prefer r and delta value, let's say a is r cosine delta and b is r sine delta. Okay, then like this ut, which was a cosine omega t plus b sine omega t can be written by r cosine delta times cosine omega t plus r sine delta times sine omega t. Okay, then like for here, what I'm gonna do is like we can use one important like trigger function property, which is cosine x minus y can be written by cosine x cosine y minus sine x sine y. Okay, when I apply this one, then this can be written by r times cosine. Let me write omega t first and minus delta 4. Okay, so where your r is square root of a squared plus b squared. Okay, and your tangent delta is equal to b over a. Okay, wait a minute, where this came from? Okay, it's really easy. Let me show it to you. Okay, I'm not gonna highlight it. Okay, there we go. Like since we define a as r cosine delta and b as r sine delta, then a squared plus b squared is equal to r squared cosine delta square delta plus r squared sine square delta. That is r squared times cosine square delta plus sine square delta. Okay, look at that. There is a trig identity, right? So that is equal to r squared. So finally, we can say r is equal to square root of a squared plus b squared. Okay, and what about this guy, tangent delta? Well, tangent delta is equal to sine delta over cosine delta, right? If I multiply r over r like that, then your numerator will be r sine delta, and your denominator will be r cosine delta, which is equal to b over a, okay? This is the way to find delta and r, okay? So, well, when I check your Weber sign, when I check your infinity problem, okay, one of the problem is concerned with this technique, okay? So don't forget this one, we're gonna apply this one for that problem, okay? Let me move to the example number 1 first, then we're gonna come back to here, okay? Here we go. So for each of the following, determine omega 0, which is the frequency, and r, which is concerned with amplitude, and delta is the phase, right? And also we can find the like period as well. So look at that. There is like a combination between like cosine and sine function, right? And we'll do the same thing. Okay, here we go. So like in the previous slide, we talked about this one as a, which will be defined by r cosine delta, and -6 will be b, which is defined by r sine delta, where the r is equal to square root of a squared plus b squared. We already derived this one, right? And tangent delta must be equal to b over a, okay? Then, okay, here we go. Then let me try to find r and delta first. No. Like whenever you define like this way, this will be r cosine 7t minus delta, right? Definitely your omega 0 is equal to 7, okay? So like whenever you find r and delta, then we can plug in here, okay? Here we go. Your r is equal to square root of a squared plus b squared, which is equal to square root of 1636. That is 4052. Then when you just simplify a little bit, and it can be 4 out and 2 square root 13, right? Okay, this is like your r. And what about delta? And actually, like your delta will be the like in the tangent inverse of b minus a. Okay, but for this case, you have to be careful. Okay, look at that. And since your cosine delta is positive, do you understand what I'm saying? I'm talking about a value. A is 4, and r is positive. Then cosine delta must be positive. And let's look at b. Okay, your sine delta is what? -6, which is negative value. Okay, and look at that. Then we can say your delta is in which quadrant? Like cosine positive cosine value and negative sine value, which is like the first quadrant, okay? So, okay, basically like we're gonna use tangent inverse, okay? And this is proposed for tangent inverse find the tangent inverse value, okay? Since the domain of tangent value on your calculator, or like, in general, the domain of tangent function will be from -90 to 90. Does it make sense? So, like, whenever you do like tangent inverse of b over a, that value will be negative angle, which is in the like in the second like fourth quadrant. Does it make sense? So like, but in this problem, your delta must be between 0 to 2 pi. Okay, so we have to convert that into like a 0 to 2 pi function, to a 2 pi range. Okay, which means whenever you subtract a negative value from 2 pi, that will be your tangent value. Okay, so your delta must be equal to 2 pi plus tangent inverse of -6 over 4. Okay, or if you want to take care of the sign by yourself, you can do like this way as well. Okay, and that's it. Okay, then we found like all the delta and R as well. Then now we can answer like all the question of this problem. Okay, so here we go. So first of all, do they ask you something? Oh, that's it, right? Then like you can plug in this one into like the problem. Okay, so now let me come back to the. Okay, there is another one. Okay, but we're gonna talk about this one like during the class time. Okay, and also like you can try to do by yourself. Okay, so let me come back. So we are almost there. So we were here, and since we find like cosine function, like function form, then now we can draw the like graph of your like oscillation motion, right? Let me rewrite my general solution is equal to R cosine omega t minus delta. Okay, so well, like in my note, like given graph is not that we not like you cannot understand very well because like you look at that, your x-axis is not t but omega t. Okay, so that's why like I would love to make a new one. Okay, with like t and u. Okay, then definitely your amplitude is r, and then like your frequency is omega. We talked about amplitude already, right? And then like the period is definitely 2 pi over omega. Okay, so since your phase is delta, like your second like highest point will be delta plus 2 pi over omega because that is the period. Okay, and these are everything. The main issue is, okay, let me try to like summarize this again. Okay, basically undamped free vibration motion is just oscillation things, right? And when it derived this motion, it was m u double prime plus ku equal to 0 form, which is a homogeneous second order linear differential equation with constant coefficient. Okay, and we can handle that because like we know about the characteristic equation, right? And when you find the solution of a characteristic equation, it was measured number, right? That's why your general solution form was a times cosine omega t and plus b sine omega t, right? And with that one, like like the main interest about that equation is finding like amplitude and frequency and period and also like phase as well. Okay, so that's it. In next video, we're going to talk about example 2, like which is the like the undamped vibration, free vibration motion. Okay, thank you.